All right, so welcome to Math 202, Vector Calculus. So this is the last quarter of calculus. I'm assuming that everybody has done basically 2 semesters or a year's worth of calculus up to this point. And we're going to pretty much just pick up where we left off. And really, we're going to be dealing with vectors. So everything this quarter is going to be about vectors, multi-dimensional stuff. So we'll learn how to do things like double and triple integrals and that sort of thing. So that's where we're going to be going. My name is Bruce. I prefer being called Bruce. I'm really informal. As you can tell, I'm wearing my Bronco jersey because it is game day. But anyway, so I'm really informal, but if you are not comfortable calling me Bruce, that's cool. Pretty much you can call me anything within reason. And anyway, so what I want to start with is just going over the syllabus a little bit to explain what you should expect to see and what this class is going to look like. So I'm going to go ahead and share my screen here real quick. Yeah. Just press the wrong button. Don't you love it? Just like someone who thinks they're all savvy, got it all figured out, pressing the wrong button. All right, let's try this again. I'm going to blame it on the fact that I just have a touchpad. I really should invest in a wireless mouse, but I'm cheap. So. All right, so on the Canvas shell, this is where you're going to find everything, obviously. I imagine most of you found the syllabus and everything. We'll talk about some of the other stuff here in a second, but let me go ahead and pop that up. So first and foremost, easiest way to get a hold of me, best way to get a hold of me is by email. I do answer my LTCC account, but I find that it's not quite as trustworthy as my alternate account. I've got a Hotmail account as well. So I prefer that. It's just my name, bruce.armbrust@hotmail.com. So that's by far the best way to get a hold of me. You can also message me through Canvas. I do get those alerts and I do check it as well. And I will get back to you within 24 hours, with the only exception possibly being on weekends or during holidays. But for the most part, I feel like I'm pretty good about getting back to you. I may not get back to you like right away because A, I've got other classes going on. B, I'm almost 50, so I'm not like that. I didn't grow up with my pocket buzzes and I immediately answer. So just realize it's not anything personal. It's just I'm an old man. So office hours, great times to find me so that we can chat about stuff one-on-one. I will be doing them on Zoom. It is a different number, a different Zoom room. But you can see there it's 11 to 12 every day, and then Thursdays I actually added an hour from 10 to 11. I don't officially have an office hour on Friday because I have a standing meeting that pops up a lot at that time. And just so you guys know, this time is right between my classes. I'm teaching Calc 1 and Calc 4. So it's right in between. But if those times don't work, if there's a better time, let me know. We can chat. We can figure out a time that works between both our schedules. Even if it's, evening or something, I really don't mind doing that as long as I've got the time and you've got the time. All right. So you guys know about class, you figured it out. But I will be recording these, as I mentioned, and they will be on YouTube. So I'll usually get them up later that day. Sometimes it takes a little bit for Zoom to process the video, and then of course YouTube needs to upload it and all that. But for example, my calc class this morning that ended at 10:15, it's already up. So that will be my goal every day, is to get those things up and ready. The textbook, for those of you who were in the sequence with us last year, it's the same one. It's OpenStax Volume 3. Basically, we're going to finish off what we didn't do last quarter. For those of you who are new to it, it costs you $0. You can get it for free. If you want a hard copy, because they do make hard copies, like I've got one here. They're really quite cheap, especially compared to other textbooks. So, but anyway, you can access it either through this link. I also put a link on the Canvas shell for you. So calculator, you probably have one. If not, at least hopefully you have access to some good things on the web like Symbolab or Desmos, that type of thing. So course grade, this is really what you care about. The usual 90, 80, 70 kind of scheme. And your grade's going to be broken down to 15% homework, 15% quizzes, 40% for regular exams, and then 30% for the final exam, which will be cumulative. But you guys are used to that by this point. I mean, all math is cumulative. We're going to be using things from last year's calculus. We're going to be doing algebra. We're going to be doing trig. So it just always just builds on itself. But the gradebook in Canvas will hopefully stay up to date so you know exactly how you're doing. All right, so in terms of the homework, you are going to use My Open Math. If you're not used to that, but you kind of know like My Math Lab, it's sort of a similar thing. It's a free service. We're going to be using that. They are all in Canvas, so I'll go ahead and show those to you just so you can see it in a minute. But most importantly is check out this last sentence. Right? If all the homework is completed with a score of at least 50%, your lowest regular exam score will be dropped. Okay, so do your homework. Not only is it counting towards your grade, but it's going to take some of the pressure off exams. And I know for a lot of students, it makes it so they don't even take exam 3. They're happy with their first 2. But anyway, so make sure you keep doing your homework so you can do that. The homework assignments are all due Monday at midnight, technically 11:59. Don't push it. But they're all due at midnight on Monday. So it's basically, think of it as weekly assignments, multiple sections, but one due date per week, give you a little more flexibility, allow you just time to deal with it because of whatever else may be going on. So quizzes, there are going to be 6. And this is usually where people who know me laugh. Because while I schedule 6, how many are we really going to have, Jacob?
Not many.
Yeah, probably like 4. I put them all in, and we'll see how those roll. But I will drop your lowest quiz score, no matter what. And quizzes will be done at the beginning of class. So you'll notice that I set this up so that they start at 1 p.m. They'll be available starting at 1 p.m. on quiz days. But then you need to upload a PDF of it by 1:40. Because at 1:40, we're going to start up lecture and continue. So it's just like being in class. I'm basically giving you the half hour to do the quiz and then the extra little bit of time for dealing with technological issues. And then exams are going to be similar, except when you take an exam, we're not having class. So you have a longer period of time. You basically have the full class period. I consider it 2 hours. So you've got 2 hours for the exam and then an extra half hour to deal with any technology. So don't push those either. Like I'm not trying to make it so that you've got 2.5 hours to take the test. You've got 2 hours to take the test and then the rest of the time to sort of deal with whatever happens. So try not to push those. The final exam has a slightly different time. I'll talk about that in a second. So that registration info is just there so you can reference it. You guys know how to succeed in a math class. But I do want to point out that the tutors from LTCC are going to be up and running. You can find them through Cranium Cafe, and the link is right there. It's the library, basically, is all the library services are through there, including math tutors. But I will tell you, I'm not really sure how many tutors we have that have been through this class?
There's 2. Dom and
Two?
Braulio are
Was it
still
Bradley? Do you
tutoring.
know?
Yeah, Dom and Braulio.
Okay. So for those of you who are kind of newer, you want to seek out Dominic, Dom, and Braulio, because they both have gone through the entire sequence. And so they know this course. They also know me, so they know what kind of approach I take and all that. So definitely make use of them, but also make use of me, right? Think of my office hours as tutoring sessions, but with a expert. So.
Chad too.
All right. So then if you are a DRC student, please let me know so that I can work with the DRC and help set up your accommodations. And the sooner I find that out, the better. Also, I put the information for the library here. Realize that you can get other stuff there, not just tutoring. But I also put their hours, and they told me that math tutoring is going to be available during all hours. But if you're going to be restricted to just finding Dom and Braulio, you're going to be restricted to their hours. So I will see if I can figure that out. And maybe Bradley, you can look too, because I imagine you have access to like the schedule and stuff.
Yeah.
Maybe you can pass that on to me, and then I can put it up on the Canvas shell.
Sure.
That way, everybody can find help when they need it. And then this last thing, academic dishonesty. Obviously, when you're taking exams and quizzes, I can't watch you. I kind of have to trust that you're doing it yourself. And so I put on here that cheating also includes using online resources to do the problems for you. And I don't mean don't use Desmos to draw a graph. That's not what I'm talking about. What I'm talking about is where you go to like Symbolab and you type in the integral and just hit enter, right? And then Symbolab spits it out. That's cheating. That's no different than asking the person sitting next to you, how do I do this problem, right? And I can tell, believe it or not, I can tell when people use those things because they are computers and they don't approach it like people. They just don't. And I've been teaching calculus for about 25 years. So I've seen just about every approach to every problem. So I can tell, just don't do it. And this isn't a lecture I really need to give you guys because you know that it's important for you to learn this math. You're not taking this just for the hell of it, right? This isn't, you're knocking out your gen ed math requirement. I think that'd be funny. Sounds like, oh yeah, no, this is my gen ed math, vector calc. But you're all gonna be using it, whether you're a math major, physics major, engineering major, you know, whatever it happens to be. Bits and pieces of this are gonna be relevant later. And it will definitely, it definitely behooves you to learn it, not just learn how to make something else do it, because you won't always have that available. Anyway, I told you you didn't need the lecture, and yet I gave you the lecture. All right, so course schedule, and at the very top here it says this is tentative, because it will change. It's just a question of how much it changes. But on here you'll see there are quizzes and exams. The quiz dates are most likely dates. The exam dates are going to be the exam dates. However, I imagine quite a few you are taking physics with Kathy right now. Is that right? Yeah.
Yeah.
So double check her syllabus because you guys don't meet till tomorrow, right? So.
I think we actually meet at
Right
3
after
o'clock
this.
today. Yeah.
Oh, you guys are today? Okay.
Yeah.
Well, double check that. And if we end up having our exams on the same day, which happens, not a lot, but if it's set up that way, let me know so that she and I can talk and maybe adjust things slightly. especially if it's like back-to-back day. I don't want that to happen because that would be pretty brutal. But barring that, the exam dates, you can go ahead and put in your calendars, have Google remind you, because that's when they're going to be. The only thing that might change is the content, right? What exactly is on it. So those dates are for sure, right? So you see the first one's not till October. So we got about a month anyway. But then a couple of things to point out. On Monday, November 9th, we will not have class. The college is closed for Veterans Day. And even though we are not at the college, we are still going to honor that. So we will not have class on November 9th. And then similarly, the entire week of Thanksgiving, so the 23rd through the 27th, will be off as well. So plan on those being days when you don't have to log into Zoom and you can do whatever else. But anyway. And then lastly, the final exam, it is on Wednesday, scheduled for Wednesday, December 9th. And the exam schedule, the final exam schedule technically for us is to start at noon. So you'll notice that the hours for this exam are bumped up an hour. So noon to 2:30 instead of 1 to 3:30. I try to honor the final exam schedule because you might have a class that has a final exam at the next time block or something like that. But I'll also be quite happy and amenable to adjust that back to class time if that works better for everybody. So we can kind of play that one by ear. All right, so that's a little bit about the syllabus, but now let me just show you a couple of things here in terms of assignments. So assignments is probably where you want to go, or where you will go like 90% of the time. The other 10 will probably be the grade book, but under the assignments, you'll see that there's an assignment for each section that we're covering. I didn't mention this when I talked about the schedule, but we're not doing chapter 2 or chapter 4. You'll see that we're doing 3, 5, and 6. And yours won't show this because this is the teacher view, and since these aren't published, you won't see them. But you will see a little bit of stuff from chapter 2, but it's mostly just the readings, because this is stuff we talked about last year, or you talked about last year, hopefully at some point. I'll do a little bit of chapter 2 review today. I want to remind you about things like how vectors work, dot products, cross products, the more functional stuff. Not going to talk like about planes or the quadric surfaces or things like that. But I'll give you kind of a little review of 2 today, but we're not actually going to be doing it. But anyway, so you'll see like chapter 3. So for example, you just click on one, let's go to 3.4. And it'll bring you to the My Open Math. My computer's really slow today. There we go. So it's pretty straightforward, right? So here you go. Here's a vector function. Find the velocity and acceleration vectors at t equal 1. All right, so we'll go ahead and enter them in. I'm going to make one of them right, and one of them wrong. All right, so let's see. This will be -3, -8, 12. And then for the other one, let's just do 1, 2, 3. Okay, so you submit your question and you'll know right away. It'll tell you. You'll notice that this one I got the green check mark, and then I got my red X. So I got my velocity right, I got my acceleration wrong. All right, so I can try a similar question. Let me do another one to try to get more points. I, of course, can always move on to my next question. You can also go question to question. So you want to jump to question 7, Anyway, so it's pretty easy. And then once you're done, just hit done. And it stores your grade. So you notice right now I've got 1/2 out of 14 points. So I'm kicking butt. This is going to be probably the best homework score I get all quarter, because it's the only homework score I get all quarter. But anyway, so it's really easy, and you can always keep track of how you're doing by looking at your grade. So in terms of when they're due, again, you notice I said they're all due at Monday night at midnight. And I put the due dates on every single one of these assignments. So if you go to the Canvas calendar, it should all be in there. And it will also say it next to the assignments. Let's go down to one actually turned on, right? So here you go. So September 21st at 11:59. So in terms of the first week, there's only 2 sets that are going to be due the first Monday. And it's going to vary. It's going to be similar like that, 2 or 3 sections every week, kind of depending upon where we are in the schedule and everything. So for those of you who came from our sequence, vector calc is way slower pace. You may have remembered at times last year in calculus, you were like, holy crap, we are flying way too fast. That's going to change. We're going to go much slower. So hopefully that will help us get it down.
Bruce, I have a question.
Yeah, go for it.
Is there limited attempts for the homework problems, or is it unlimited?
Nope, it's unlimited.
Okay.
So you can keep trying them again and again and again. So there really is no reason not to get, in the high 90s or 100% on every single one of them. I mean, it's just going to be a matter of time. Obviously, if you start the thing at 11 o'clock on Monday night, you may not get to it all, but yep, take it as many times as you want. The quizzes and the exams, they're just going to be kind of like normal. You write them out and then scan them and send them in, so it's a one-time shot. But the homeworks, since it's practice, yeah, you can do it as often as you'd like. All right. Any other questions about kind of the setup or the syllabus? I'm going to go ahead and stop sharing. Nope. Okay, cool. Well, then we're going to go ahead and start some, well, not calculus really. We might get to a little bit today. But let's review vectors. Let's talk about a little bit about how they work and some of the things we do with them. And then we'll start preparing ourselves for vector calc. So let me get out of the way here.
Do you know how close I was to wearing my Raider jersey today, Bruce?
But you didn't want to lose the points?
Yeah, I really thought
That's
about
smart.
it. I'm not joking. I really thought about it.
Well, you never really want to start in the hole, right, Bradley?
No, you don't.
Yep, it's sorry about that game yesterday. Sorry, not sorry, but you'll probably be able to tell me the same thing on Wednesday. So. All right, so vectors. You guys all remember them, I'm sure. And so let me just remind you about a couple of things. Hold on a second. Is that better?
Looks good.
You can read if I'm here.
Mm-hmm.
All right, so vectors. I'm just going to do everything in 3D because why not, right? 2 dimensions is the same as 3 dimensions. So we're going to go to generic 3D vectors. So remember how we do this. We're going to have a couple of different notations that you might see. So the first, this is a notation I'm going to use all the time, where we're going to have a vector with 3 components, A, B, and C. So A is your X component, B is your Y component, and C is your Z component. Now, an alternative way that you might have seen this is as AI plus BI plus CK. These are both equivalent. The only reason I do the first one instead of the third one, well, two reasons. One, I think it's less messy, but two, it's less writing. And for those of you who really know me, I'm terribly lazy. And so I try to do as little as possible. So that's why I use this notation, right? So think about if we've got our usual grid here with X and Y and Z coming out of the board, right? So positive Z is coming out from the board. Then these components just tell you which direction to go in those different, or how far to go in those different directions to create our vector. So like if we had the vector, let's say 1, -1, 2, this would tell us we're going to go out one step in the X, we're going to go down one step in the Y, and then come out 2 steps. So that vector would point from the origin in this general direction. Right 1, down 1, out 2. All right, so there's our 3-dimensional vector. If it's just 2 dimensions, it's even easier because those we can represent on the graph pretty simply, right? Like if we just had 1, -1, that would be this vector right here. All right, so has everybody seen this? We're all good with notation and everything? All right, so the I, J, and K, just remember that those are unit vectors. They're length 1, and they just point in the positive X, Y, and Z direction. And so this is basically just lining those up head to tail and giving us our resultant, A, B, C. Okay, so operations with them. So first of all, add and subtract. This is by far the easiest thing to do because literally you just add and subtract the components, right? So if we have something like 3 - 1 and we subtract the vector 2, -2, 3 - 2 is 1, -1 minus -2 is 1, so that resulting vector is 1, 1. So adding and subtracting, we love doing that because it's just a matter of adding and subtracting the respective components. Okay, but then there's multiplying. And with multiplying, this gets a little bit weird because there are 3 of them. The first is scalar multiplication. The second is the dot product. And the third is the cross product. All right, so scalar multiplication, this is when we take a scalar times a vector. So also for those who don't know me, I'm going to draw the arrow above anything that's a vector. You do see that in some textbooks. A lot of other textbooks use bold. I can't really do bold on the whiteboard. And so I draw the little arrow. Unless it's clear, unless it's obvious, then I won't draw something. But like in this case, C is a scalar, so just a regular old number, and B is your vector. So the dot product, this is when we take 2 vectors and we dot multiply. And for this one, the result is a scalar. So when you dot 2 vectors, you get a number. You just get a plain old number. The cross product, we use that little cross for the multiplication, little x. And for this one, the result is a vector. So that's why we actually have two different kinds of multiplication between vectors. We've got the one that leaves us with a scalar and the other that leaves us with a vector. All right, so let's talk about how we do all of these. Let's remind ourselves, because we're going to need to be able to do them later. All right, so let's start with scalar. So this would be something like 3 times the vector 1, 2, 3. All right, so quiz for class. How do you do this? Or even what's the answer?
It's 3, 6, 9.
All right, thanks, Jacob. So this is 3, 6, 9. And really all you do is you just take each of the elements, each of the components of the vector, and you multiply them each by the scalar. So in this case, 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9. So procedurally, it's really easy. But what does it do? Like, what is this doing to this vector when we multiply it by 3?
It scales up its magnitude while keeping direction the same.
Yeah, it changes the magnitude. When you multiply by a scalar, you're changing its length, changing its magnitude, but you don't change the direction. So that's kind of important. Let me put that down here under scalar multiplication. Okay, it changes the length. I'm going to put here length slash magnitude. But the math term is magnitude, right? Or technically its math term is the norm of the vector. Maybe you remember that word, norm. But it changes its magnitude. We kind of want to start getting away from ideas of geometry, because you're going to see next quarter when you're in linear algebra that the magnitude of vectors, or the vectors themselves, don't have to live in 3 dimensions. They don't even have to be arrows like you think of. Little spoiler, cover your ears if you don't want to know this. But vectors could be matrices, polynomials, functions. There's all kinds of things that are actually vectors that aren't arrows. But that's for next quarter. All right, so it changes the length, but it's still parallel, or it keeps the same direction. So I'm going to put here parallel, because it technically can change the direction. Can anyone think about a scalar multiplication that actually changes the direction of the arrow?
A negative one? A negative
Yeah,
number?
if you multiply by a negative, it takes it and it moves it the other direction. So that's why we don't want to necessarily say the direction doesn't change, but we can say that it's going to be parallel. So even if it points in the opposite direction, it's still parallel to the one before. All right, so really, we use scalar multiplication for this first thing, for changing lengths. That's our goal, or if that's our goal, we want to change the length of a vector, we multiply by a scalar. And you may remember doing that to find unit vectors. Let me just do that real quick, remind you about that. Like, let's say this is a vector v is, let's say, -1 to -3. And what I want is a vector of length 1 that points in the same direction. So that would be its unit vector. Does anyone remember how to do that?
you divide by the magnitude of the vector, right? Or the square root of the magnitude.
All right, so you were right
Like
the first
that.
time, Jacob. It's
Okay.
just the magnitude.
Okay.
So you're going to take V and divide by the magnitude of V. And that little double absolute value, that's the magnitude. And that does have a square root in it, because it's basically the distance formula. So in this case, the magnitude of V is the square root of -1 squared plus 2 squared plus -3 squared, which is the square root of 14. So what we're really doing is scalar multiplication. We're taking 1 over the square root of 14, and we're multiplying it to -1 to -3. And in this case, it's actually shrinking the vector. It's not lengthening it, because this is less than 1. So if your scalar is less than 1, it shrinks the vector. If the scalar is bigger than 1, it lengthens it. So we would end up with -1 over root 14, 2 over root 14, and -3 over root 14. So this vector, u, points in exactly the same direction as v. It's just only length 1. All right, well, that's why we care about scalar multiplication. It's just to change lengths. All right, so good for that? All right, let's talk about product. All right, so let's just start with a pair of vectors and see if you remember how to do the dot product. So let's say that u is -2, 1, 0, and v is 4, -8, 1. Okay, so there's a pair of vectors. What's the dot product?
Don't you multiply each of the vector components and then add them together?
Yep, that's exactly right. So Victor, I see you put that in the chat as well. Literally what we do to get u dot v when it's in component form is we take the x components and we multiply them. So -2 times 4. We take the y components and multiply them. So 1 times -8. And then we take the z components and we multiply them, 0 times 1. And then each of those products we add together. So this is going to give us -16. And it works exactly the same in 2 dimensions, right? You just have the 2 components. So like if we had u as 1, 2, and v is 6, -3, we would get that u dotted with v as 1 times 6 plus 2 times -3, which is 6 minus 6, or 0. Okay, so that dot product was 0. This dot product is -16. If vectors were larger dimension, like if we could imagine this in the 4th dimension or 5th dimension with 5 components, you do the same thing, multiply each of the 5 pairs, and then add them up. So procedurally, this is almost as easy as scalar multiplication. All right, but why? Why do we care about the dot product? What do you guys remember? Anything?
Can't you find Isn't it somehow related to the normal vector to two vectors, the dot product? Yeah.
Something about something with normals.
I know it sounds really vague and stupid.
No, I know exactly what you're going for, but you're actually thinking about the cross product. All right, so Ralph, there you go. We use it to find angles. That's one of the primary uses of it. There are lots of things that it tells us. Lots of things you can use the dot product for. But one of the things that we use it for is to find the angles between vectors. So there's another way of looking at the dot product. And as soon as I write this, those of you who have taken some physics will go, oh yeah. So some of you recognize that. U dot V is equal to the magnitude of U times the magnitude of V times the cosine of theta. Yes, no, maybe. Can't remember that.
Yeah, that's what I was thinking about.
Okay. So basically, if these are U and V, then theta is the angle that's in between them. So this is one of the primary uses of the dot product. So remember when I did those computations and I got some numbers? That actually tells me a little bit about the angle in between them. Like when I got that the dot product was equal to 0, the only way that this can equal 0, assuming that the magnitudes are not 0, which they were not like 0 vectors, is if the cosine is equal to 0, and cosine is equal to 0 when theta is pi over 2. So this tells me that they're perpendicular. So we also have some other names for this. So I'm going to put here AKA, also known as orthogonal. And another one we use is normal. So I think that's kind of where you were going, Jacob, a bit with the normalness. Okay, so these are other names. These are the more mathy names. The one that we really want to work with is orthogonal. Because perpendicular, we kind of need to be able to see it. And it's hard to imagine perpendicular if we're in some weird space or our vectors are matrices or something like that. Okay, so if it's equal to 0, I know they're perpendicular. If this dot product is positive, then this tells me that it's an acute angle. So I'm getting a first quadrant angle. I'm getting something less than pi over 2 or 90 degrees. And then similarly, if U dot V is less than 0, if it's negative, then this is an obtuse angle. And that just comes from cosine. Cosine's positive in the first quadrant, so for acute angles, it's negative in the second quadrant for obtuse angles. All right, so that's probably the biggest use of the dot product is to find angles. But it's not the only one. Don't make me pick on the, like 6 of you that took physics, that I know took physics. Do you remember using the dot product in physics?
Yes.
Rotation.
Yeah. It was like the right-hand rule relating to that, right?
I think you're going cross product with
Again,
rotation.
God,
I know it was months ago, just felt like years ago. Not collisions, Victor. So I'll give you a hint that the kind of problems that we use dot product for primarily were ones that required a lot of work. Not electricity. At least not the example that we saw, Ralph.
was it problems relating to work?
It was work, yeah.
Yeah, okay.
Yeah, I was about to say you just gave it away. Like, what else is there?
But that was the joke, right? Because all physics problems require a lot of work, but only work problems. Yeah, okay.
Okay.
So another place we used it was work, right? It was you take your force and you dot it with the displacement. So it was F dotted with D. There are others. There are for sure others, but that was the primary one that we saw. And we also saw this in calculus back in the day. So I'm going to put dot, 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 because there's more. But these were the primary uses that you've seen. All right, so dot product, we feeling all right with it? Kind of remember it? If I made you do some dot products, you could do it. I'm going to take that as a yes. All right, cool. I see some thumbs up. Thank you. Okay, so cross product. Okay, so this one, we're going to take two vectors and cross them, and we're going to get another vector. Okay, so W is a third vector instead of a scalar. All right. So let's jump into the how do we do it. So let me give you two vectors. Let's say that we've got U is 1, 0, -1, and V is 0, -2, 3. And I want to get U cross V. Now, if this is a dot product question, it'd be piece of cake, right? The dot product, 0 plus 0 plus -3 is -3. All right, so Victor just says it's the discriminant of a 3 by 3 matrix. Okay, so you're definitely on the right track. The word is determinant. Discriminant is the part of the quadratic formula that's below the radical. So it's the determinant, but you're definitely on the right track. What does that 3 by 3 matrix look like?
So on the top row, IJK, second row, U1, U2, U3, third row, V1, V2, V3.
Perfect. So we're gonna have I, J, and K. And then we put our U, 1, 0, -1, and then our V, 0, -2, 3. And we find its determinant. So this is mostly for those of you who are new to me. But actually, I don't know that any of you know how I do this. I call it playing asteroids. Okay, and seeing Jacob's face makes me think maybe I've not shown you guys this. So those of you who are new to me, I am a child. I'm a child in an adult body, but I'm a child. I think about things in really kind of weird childlike ways. Like, for example, parabolas, you have two types. You got happy and you got sad. And I bet you can figure out which are which, right? So this is kind of how Bruce thinks. So when I find determinants of 3 by 3 matrices, I play asteroids. Now, in order to do this, you need to know how asteroids works. So I don't know if you guys have ever played asteroids. I'm a child of the 80s, so I played video games like crazy. But asteroids works like this. So you're flying around trying to shoot asteroids. When you come up and you come off, say, the top of the screen, so here comes my ship coming off the top, it immediately comes down here and continues in its same path. So it's like the screen wraps around from top to bottom, or vice versa. And the same thing happens on the sides. So if we're cruising along over here, we get to the edge, we immediately teleport over here, so the same spot vertically, moving in that direction. All right, so basically, the world of asteroids is a donut, right? Think about your classic cake donut that Homer Simpson likes to eat. That's a torus. And that would be what it would look like if you were to cut it on one end, unwrap it, and then slice the other end and unwrap it. It would look like this screen, and you would continue around. Okay, so basically it's 2 circles. That's a torus. Anyway, all right, so that's what happens when you play asteroids. So when I find my determinant, I'm sure you guys know about the going down in diagonals thing. If you haven't seen that, here's a great way of finding your determinant. So I'm going to start here with I. I'm going to come down to 0 and then to 3. So this tells me I'm going to take 0 times 3 times I. So then I go to J and I do the same thing. So I'm going to get J times -1, but now here's where asteroids comes in. Notice that I hit the edge of the screen. So I want to continue in that same direction, but in the asteroids world, I just wrap around over here. So I'm going to get, let me actually write them in the order that we hit them. So we had I times 0 times 3. We're now going to get J times -1 times 0. And then if we go to K, keep going down to the right. I got to wrap around to the other side. So I get K times 1 times -2. And unlike at school, I better not write on the walls. At school, so I get in trouble with my boss, big deal. At home, I get in trouble with my wife. That's a big deal. All right, so there's those 3. Now, we also have to subtract when we go the other direction. So think about K. I hit 0 and 0, so I'm going to subtract K times 0 times 0. I get J times 1 times 3, so I'm going to subtract J times 1 times 3. And then with the I, I've got -1 and -2, so I times -1 and -2. All right, so we're ready to get this. I've got 0 -2 leaves me a -2i. For the J, I have 0 -3. That's -3. And then K, I've got -2 minus 0, which is -2. All right, so that's how I do it. I play asteroids. Just think anytime you're going down to the right, those are terms you're adding. Even if they're negative, you're still adding the negative. And then when you're going down to the left, those are going to subtract. All right. So there are other ways of doing the 3 by 3 determinant. I just find this to be really fast. You do this a few times, you'll get it, and you won't have to think about it. All right, so doing the cross product, way more difficult. Dot product, simple. Scalar product, really simple. Cross product, not so much. But the cross product is incredibly useful. All right, so first thing I want to point out about this is there's something special about this vector. Anybody remember the relationship between the cross product resultant and the original two?
Orthogonal.
Yeah, that's the biggie. So with the cross product, let me just put this here. So the result is orthogonal to both u and v. So it's always going to be perpendicular to the plane that holds u and v, right? So any two vectors, they lie in a plane somewhere. And so u cross v is going to be orthogonal to that. So it's perpendicular to that. So this is actually one of the uses. You can use this to find the normal vector of a plane. So when you did that 3D geometry stuff and you found equations of planes, what you could do is actually find two vectors in the plane, find the cross product, and that gave you a normal vector. And normal vectors to a plane are unique. There's only one, right? If I've got a plane here, and I've got a normal vector, right? It points in one direction. Yes, it could have different lengths, so we often use the unit normal vector, but that's good enough, right? And so if I change my plane, I change my vector accordingly. So if I find this vector, I know this plane. All right, what else do we use the cross product for? Remember anything else?
Torque.
Okay.
Yeah. Right?
So in physics, for sure, torque was a big one. And I'm just going to put here rotation, because I don't remember who that was. Bradley, Jacob, maybe both of you, I don't know. Mentioned rotation. And rotation stuff uses torque all the time. And that is where we use the right-hand rule to figure out what direction it was spinning. You can also use that to figure out which direction your cross product is pointing. So real quick, the right-hand rule, make sure you use your right hand. If you put your index finger in the direction of u, your middle finger in the direction of v, then wherever your thumb points is the direction that it's going to be pointing, right? So like if u cross v, then that one's going to be coming out this way. If I had to turn around u, v pointing down, let's say, then my thumb is going to go in this direction, so it's going the opposite. So you can use the right-hand rule. You can also curl your fingers from u, curl towards v, and then your thumb points in the right direction. So we use this a lot for torque and rotation. You will definitely see this in E&M if you're taking that this quarter with Kathy. So definitely a lot of physics examples. And then I see Ralph put in here, you can use it to find angles, and then, but why? And that's exactly right. It turns out that you have a similar relationship. If you look at the magnitude of u cross v, that's equal to the magnitude of u times the magnitude of v times the sine of the angle in between them. So that looks a lot like what we saw for dot product. So you can alternatively use this to figure out the angle in between two vectors instead of the dot product. But I like Ralph's there, but why? Right? Why would you do it, since finding the cross product is so much more difficult? Plus then after you find that cross product, you got to find its magnitude. That's all kinds of no thank you.
The camera, just by the way, is getting a little bit blurry. It might be shifting out of focus a little bit.
Mhm. I'm going to stop video for a second. Let me just check my settings. All right, let's try it again.
That's better. Yeah.
Is that better?
Yeah.
Okay. You know, the classic turn it off and on again fixes everything, right? It's either that or plug the stupid thing in. All right. So for us, by far, the most important thing about the cross product is that it's orthogonal to both u and v. That's probably the thing that we care most about, other than the specific instances where cross product is useful in like a physics example. But in the math world, it's the fact that they're orthogonal. All right, so how are we feeling about vectors? Kind of dusting off the cobwebs, coming back a little bit. All right. Well, then let's go ahead and start into Math 202. Let's actually start doing some new stuff. And basically where we're going to start here in chapter 3 is with what we call vector value functions. So again, because I'm lazy, I'm going to call these VVF. So if you ever see me write VVF, that just means it's a vector valued function. All right, so what is this exactly? Well, it's a function. So we already know a little bit about functions, right? Functions are basically rules of assignment. We start with something and we get something else out, right? We got our domain and our range. And what we know is that any range element, like when we put in a domain element, we get one range element. Okay, well, I'm going to start here that the domain of a vector valued function, this is a real number. So with vector value functions, we're plugging in real numbers. You're used to that. What you may not be used to, I'm going to give you some new notation. So this is a capital R with an extra vertical line on it. And that's what we do to show that it's a real number, right? The set of real numbers. And real quick, Victor, you say cross product only works in R3 with 3 dimensions. That is correct. For cross products, you have to have 3-dimensional vectors. So if you've got 2D vectors, you basically just throw the 0 on as your third, and then you can do the cross product. So yes, that is correct. Okay, so our domain for vector valued function, real numbers. But what we get out of this is a vector. So you're putting in a number and you're getting out a vector.
That example you did on the homework when you were showing us how it works, was that a vector valued function?
Yes. Yep, that absolutely was. So basically, this is how you're going to see vector value functions. You're going to have, instead of F, we use R. I don't know why, but it's kind of standard that we use R. So we're going to have R of t. So I'm putting a little arrow over this to tell us that this is a vector value function. We're plugging in a t, and what we're going to get out is a vector. And so there has to be a rule for how to get the different components. So we could have something like t squared, t minus 1, and then how about e to the t. So this is a vector value function. We plug in a t, we get out some vector. So for example here, r of 0 would be 0, -1, 1. It's a vector. I don't have choices, so it is a function. And it's completely determined by what number I plug in. Right? So that would be r of 0. We could use, say, r of -1. In this case, it would be 1, -2, e to the -1. So in just like a real quick inspection of them, they probably don't seem that complicated because they're not. I mean, it's basically what you do with regular functions. It's just you're attacking each component separately. So what you'll sometimes see, if we do this generically, is we'll just write out each of the components as a separate function. So there's a function that determines the x component, a function that determines the y component, a function that determines the z component. So you sort of slap them all together, and that gives you this guy. So they're functions, so fundamentally they're the same. It's just before, the functions you were used to dealing with were ones where you plugged in a real number and you got out a real number. Now we're getting out a vector. All right, so how are we doing so far? Make sense? All right. So what we need to do is basically, now that we've got these things, now that we've got vector value functions, we need to start thinking about them in the calculus world. So I want you to go back to the very beginning of calculus. So for some of you, it was like a year ago right now. As we started gearing ourselves up to doing calculus, what did we look at with functions? What were the things we were
Continuity.
concerned about?
Limits. Oh,
Yeah.
continuity, yeah.
So limits, continuity, all that kind of stuff. Well, we need to do the same thing here. Like our goal, our eventual goal is to get to doing calculus on these, finding derivatives and all that good stuff. But in order to create derivatives, we have to talk about limits. We have to talk about continuity and everything else. So let's kind of start from scratch. And let's talk about domain. Let's talk about range. Let's talk about limits and so on. Okay, so how do you think we find the domain of one of these things? What do you think we have to do to find the domain? Okay, so then Victor says, look at each function domain and combine them. So let me make sure I understand what you mean in your chat. When you say each function, do you mean the functions that compose or create the components? Yep, okay. And that's exactly what to do. When we want to find the domain, think about what that means. We're looking for t values that make each of the components, or that make the function work. For this function to work, for this function to be defined, each of the components needs to be defined. So it turns out that the domain of this thing, it's the intersection of the domains of the component functions. So again, think about what Victor said. What Victor said. I just had a horrible airplane moment. If you've ever seen the movie Airplane, you know what I'm talking about. Sorry, Victor. Except maybe we'll just change your name to Vector. What do you guys think? Is that a good name for Victor? All right. So from now on, Victor, your name's Vector. We good with that?
Does that say intersection?
Yes.
Okay.
All right. Looks like he's good with it. He just changed the spelling on his name. So. All right. So basically, we'll just look at each one separately, like Vector said, but then we're going to find the intersection. That's how we're going to combine them. We can't just like stick them all together and do a union. We actually need the overlap. Because suppose that there's a number that works for F, but doesn't work for G. As soon as it doesn't work for G, we got to get rid of it. Same thing, if there's something that doesn't work for H, it's gone. So you basically just eliminate anything from F, then you go to G and find out, is there anything else we got to get rid of? Then you go to H, and so on, until we're left with only the things that work. All right, so let me give you an example here. So let's say that this is our vector value function. Let's go with natural log of t, comma, cosine inverse of t, comma, 1 over t minus 1. So I tried to find things that have lots of issues. All right, so let's attack each of these separately. So natural log of t, what are the t's that work? What's the domain of that?
Any number larger than 1?
Any number larger than 0?
All right, so we got larger than 1, larger than 0.
Yeah, larger than 0. Or 0 and greater?
Okay, so greater than or equal to 0?
Yes, wait, right? It's natural log of 0,
Well,
1.
it does come down to 0, but it's a not inclusive.
Oh, right, yeah.
The natural log of 0 is undefined. Okay, so for that one, you can put in any positive number you want. But that's it. Okay, so already we know the domain of R is restricted to just positive numbers. Since anything 0 or lower causes a problem with the first one, we have to throw all those out. Okay, so now let's look at inverse cosine. So does anybody remember the domain of that? Okay, so Victor says
Yeah, that seems
minus
right.
1 to 1.
Yeah, negative 1 to 1, but obviously it would just be 0 to 1 here because we already eliminated negative numbers,
Yeah.
right?
Yep, that's true. But let's go ahead. We're going to write them all individually, and
Okay.
then we'll put them all together. But you're definitely going the right track. But just inverse cosine itself was just between minus 1 and 1. So we can only include things between negative 1 and positive 1 inclusive. So you're right. If we're kind of playing along as we're building this, let's do this. Let's draw a real number line. And let's talk about what we've eliminated. So somewhere here is 0. So already from the natural log, we eliminated all of that, right? So we can only be 0 to infinity. Inverse cosine was -1 to 1. So just from those two, we're somewhere in here. So then the question is, well, what about the last guy? Well, that one's nice and easy. The domain of that is just everything except 1. So once we put that all together, what's the domain of R?
Is it 0 to 1 non-inclusive of 1? Or 0?
Perfect. So the domain for this vector valued function is everything between 0 and 1, not including those endpoints.
Makes sense.
Does that make sense?
Yeah.
All right. So basically do each one independently and then look for the overlap. All right, so not really that big of a deal. Just think of it this way. When you found domains before, you just found the domain of one function. Now we're doing that same process 3 times, or twice if it's just a 2D vector, right? But this one is going to be 3. And then we just have to make sure that we find their overlap. All right, so cool. We now know how to find the domains. In terms of the ranges are just going to be a set of vectors that pop out. They're a lot more difficult to describe because before, when you just had a regular function, think about the range, it was a set of real numbers. We could represent that on the real number line. Now, the range is a set of vectors. What are all the different vectors that can come out of this? Oh, good Lord, tons. And trying to describe that's a little complicated, so we tend not to. All right, so there you go. There's domain. So what about limits? What about finding the limit of a vector value function? All right, so first, realize that what we're doing when we take a limit here is we're looking at what happens as our t value, as our input, approaches some number. So just like with a function of 1 variables, back in the day when you did that limit, you're basically saying, okay, what's coming out as we get closer to this point? And back then it was a number. Now it's a vector. So we're basically going, okay, what vector are we approaching as we get closer to this t value? Okay, so this is what the notation is going to look like. We've got our vector value function, and we're just going to see what happens as t approaches some given number. So do me a favor and go back in time. When you did this back in the day, how did you evaluate a limit? What was your initial attempt always?
Trying to plug in the point.
You just try to plug in that value. Because if you could, then everything was great and it worked out just fine. If you couldn't do that, then we had to rely on other tricks. Algebra tricks like factoring, rationalizing. We could do numerical approximations. Later, you learned about L'Hopital's rule, which is like huge, by the way. So we always tried by just plugging a number in, but then if that failed, we went to something else. Okay, well, with vector value functions, it turns out that when you take the limit, it's the same as taking the limit of each of the individual component vectors. So think about this. When I talked about the domain, we saw that it was same thing as before, just got to do it 3 times. Now, same thing as before, taking limits, we just have to do it 3 times. All right, so let me show you what I mean. Let's do an example. This will also help us practice our limits. Let's take a limit as t approaches 0 of sine t over t. Let's go t times natural log of t and 4. All right, so again, just think about doing each of these limits individually. So the first thing we would try is plugging in 0. Clearly, you see this first component, we've got a problem because we're dividing by 0. The second one, also a problem because the natural log of 0 doesn't exist. The third component, no problem, it's 4. It's always 4. So every vector that comes out of this always has a doesn't matter. Well, that means we have to evaluate these other 2 limits. So how about this one? Sine of 0 over 0. Remember that limit?
Look.
I'm actually not going to do L'Hopital's. You could. You absolutely could. Because sine of 0 is 0. And 0 over 0 is an indeterminate form. But this is one you guys should remember.
1.
Yeah, it's just 1.
Oh,
Sine of 0 over 0 is 1. So that first limit is actually equal to 1.
Wait, why is that?
Yeah.
Cause? No, I'll show you using L'Hopital's rule. You can actually prove it in lots of different ways. You can use the squeeze theorem. You can use some geometry, some trig, but I'll show you using L'Hopital's rule. All right. So I said I wasn't going to do it that way. Well, I guess I am now. So thanks a lot for sharing this. No, I'm
You're
kidding.
welcome.
It's all good. All right. So let's look at that limit. So with L'Hopital's rule, so if we see sine of t over t, right, you plug in 0, and you get 0 over 0. And for L'Hopital's rule, you have to have 0 over 0 or infinity over infinity. If you're in that situation, L'Hopital's rule turns it into another limit. But what do? How do you apply L'Hopital's rule?
Take the derivative of the function.
You take a derivative of the top. So the derivative of sine is cosine. And then you divide by the derivative on the bottom, which is 1. And these 2 limits are the same. So if we plug in 0, now we get cosine of 0 over 1.
Which is just 1 over 1.
Yep. Cosine of 0 is 1. 1 over 1 is 1.
Cool.
So
Thank you.
that's probably the easiest way to show it. But that's just one of those that you see it a lot, and so you just pick it up. For those of you in physics, whenever you do the small angle approximation, I don't know if you've run into that yet. Usually you see it in like optics, but if you ever have a small angle, you can change sine of t into t. That's what this says, right? The fact that this equals 1 when t is really small means the sine of the angle is about the same as the angle itself. You can also use this for tangent. So in physics, if you're ever presented with a sine or a tangent and you know the angle is small, you can just replace it with the angle itself. It's useful, trust me. You could also prove it using power series. You want to do power series?
No thanks.
Oh, you're no fun.
No.
So you can also show it with power series pretty easily. In fact, here you go, bonus. So sine of t, don't know if you remember sine of t, but as a power series, it was t minus t cubed over 3 factorial plus t to the 5th over 5 factorial, and so on. So it was all the odd powers of t divided by their factorials. So think about what sine of t over t equals. If I divide all those by t, well, that just decreases all of the exponents by 1. And what happens if we plug in 0? Well,
It just
first
becomes
thing
1
is still
minus
there's a
0.
1. And then everything else just goes away.
Yeah.
There you go. There's proof number 2. I'd give you a third one, but I can tell you already don't care. You're already good after 1. Anyway, moral of the story, sine of t over t is 1 as t goes to 0. All right, well, now we're left with t times the natural log of t. So what about that one? All right, well, let's see what happens when we plug in 0. So that's going to be 0 times the natural log of 0. And the natural log of 0, as you get closer to 0, that number gets very small negative. So we end up with 0 times infinity.
Which is 0. No, wait.
Is it 0? Sometimes. Is it infinity? Sometimes. Is it 37? Sometimes. So this is another indeterminate form. So 0 times infinity, we have to change it into either 0 over 0 or infinity over infinity. So you may not remember this trick, but it's a really handy trick when we're dealing with limits like these. Is we can make this the natural log of t over 1 over t. So this is equivalent, right? Dividing by a fraction, same as multiplying by its reciprocal. So we've got natural log of t over 1 over t. And now you can see that this is infinity over infinity, right? 1 over 0 goes towards infinity, depending on which side we're on. So now we can do L'Hopital's rule. So let's take a derivative of the top and the bottom. So the derivative of natural log is 1 over t. The derivative of 1 over t is minus 1 over t squared. If we do some real quick algebra on this, we have 1 over t times negative t squared over 1. And that reduces down to just negative t. Which then, when we plug in 0, does give us 0. So I don't remember who it was. I think it may have been Jordan who, when I said, what do we get here? I heard somebody say 0. And that is correct in this case. But you just got to be careful. 0 times infinity, not always 0.
Why is that?
It depends how they grow, how quickly
Okay.
they grow.
All right.
Yeah, I'm going to leave it there.
I'll
'Cause
take it.
Well, I appreciate the questions, Bradley, because you're always good about this. Let me sit down here for a second so we can chat. So the thing about infinity is that different functions grow at different rates, right? So like exponential functions grow much faster than polynomials. I mean, just think about it. Take 2 to the x. You don't have to go very far before that power is bigger than, say, x squared, right? Just go 2 to the 5th versus
Yeah.
5 squared.
Yeah.
Right? So like exponentials will grow faster than polynomials. Logs grow slower than polynomials. So like in this case, we had a polynomial, t, and we had a log. That t, in terms of growth or whatever, since they're growing at different rates, it kind of makes it so that it's not getting as small as fast as the natural log. And so we end up dividing by a bigger number, which takes us down to 0.
Makes sense.
Right? But it's solely because that pairing of functions.
Mm-hmm. And if it was
So
any
if
other
we had
function,
had, like let's say you had e to the t times 1 over t. No, that's still, let's say, I was trying to think of one off the top of my head, but I can't get there. But it's all about how quickly they grow. And you kind of saw that when you looked at horizontal asymptotes of rational functions. Remember when you would do the whole look at the degrees on top and bottom
mm-hmm.
trick? It was the same idea.
Okay.
You would get limits, like in essence, you had infinity over infinity, right? Because you're looking at it as t goes to infinity of those polynomials.
Yeah.
Sometimes you got 0, and that was because the bottom was growing faster.
Yeah. So.
Sometimes you got infinity because the top was growing faster.
Mm-hmm.
And then if they were growing at the same rate, same degree, you got a nice finite number.
Yeah.
So it's all about growth rate.
Okay.
And basically it goes, well, on the very top are factorials. You may remember that from series stuff. If you ever had a factorial, that kind of drove everything. After factorials come exponentials, then come polynomials, then come logs. And then, you know, other things like tangents and, you know, other stuff like that that go to infinity, those, they don't really fit into that hierarchy all that well. They kind of vary a bit.
Mm-hmm.
So anyway, that's really why L'Hopital's rule, or that's why indeterminate forms are indeterminate, is because it totally depends how those functions are going to infinity or how they're going to 0. What I like to say to really confuse people is I like to say 0 divided by 0 It depends what kind of zeros you have.
That
Now
makes
you can
sense.
imagine
Yeah.
someone's not gone through this. It's like, what the hell are you talking about?
Well, my thought initially was like some infinites are bigger than others. You know,
Yep, that is
makes
true. Like you've got countable infinity versus uncountable. But that's not really this. This is more just
the functions doing what they do.
it's the function themselves, how they behave specifically compared to each other.
Got it.
So, but that was a good question.
Thank you.
All right, so to kind of wrap this one up, basically think about what's happening. This is saying as our numbers get closer and closer to 0. So we're at 0.1, 0.01, 0.001. Each time we're getting a vector out. But those vectors start getting closer and closer to the vector 104. Right? Put in 0.001 on your calculator and plug it in. You're going to get something that's very close to 104. Right? It won't be 1 exactly. It won't be 0 exactly. But instead of 0, maybe it's 0.0003 or something like that. Right? So it's going to get close. And the closer you get to this t-value, the closer your resulting vector is to this one. But I guess long story short, we're doing exactly the same thing we did before. It's just what's coming out as a vector. So, all right, but I see our time is up. So I think we're going to go ahead and stop here. For next time, we're going to pick up where we are. We're kind of in the middle of 3.1. So we're a little bit behind schedule already. For
My
those of you who
bad.
know me, that's not a surprise. But we'll definitely get caught up. So we'll move our attention to continuity next, and then we'll go to differentiability and what exactly that means. And in the midst of all that, we'll talk about graphing as well, because a lot of times it helps if we can visualize this stuff as pictures. All right, so with that, I'm going to go ahead and hit pause on the recording.